The inverse of a matrix A, denoted by A to the power minus 1, is a matrix which, when multiplied back with A, either to the left of A or to the right of A, gives us a unit matrix. We can find the inverse of a matrix using elementary transformations, that is, row transformations and column transformations. When we use row transformations, we start with the equation A is equal to IA, and we apply row transformations on this matrix to convert it to a unit matrix. And to maintain equality, we have to apply the same row transformations to this matrix, and in the end this gets converted to the inverse of the matrix. However, when we use column transformations, we begin with the equation A is equal to AI, and we apply transformations to this matrix here and this matrix here. This gets converted to a unit matrix, and this gets converted to the inverse of the matrix. Now, if you observe carefully, you would be able to guess that if we have two matrices X and Y, and we have a product C, if we apply a row transformation to the product, then we'd have to apply the same transformation to X, which is to the left of the multiplication sign, to maintain equality. And if we apply a column transformation to C, then we have to apply the same transformation to Y, which is on the right of the multiplication sign, to maintain equality. But is this actually true? To test that, I have example matrices A and B. A is 1, 2, 3, 4, and B is 6, 7, 8, 9. C is defined as AB and D is defined as BA, and I've done the multiplication beforehand in interest of time, but feel free to do this yourself and double check my calculations. C comes out to be 22, 25, 50, 57, and D comes out to be 27, 40, 35, 52. Now let's apply some transformations. We begin with row transformations and matrix A. So let's apply on matrix A the most simple row transformation, that is interchanging two rows. There are only two rows in matrix A, so we can only interchange row 1 and row 2, and that gives us the matrix 3, 4, 1, 2. And this changes, let me do this in a different color so it's easy to make out. This changes our product AB to 3, 4, 1, 2 times 6, 7, 8, 9 instead of 1, 2, 3, 4 into 6, 7, 8, 9. And this comes out to be 50, 57, 22, 25. And if you remember what C was, if we apply the same row transformation to C, then we get the matrix 50, 57, 22, 25. So far so good. Now let's see whether the equality is maintained the other way around, and I'll do this in a different color. Our product BA changes to 6, 7, 8, 9 multiplied by 3, 4, 1, 2 instead of 1, 2, 3, 4. This changes it to 25, 38, 33, 50. If we apply the same row transformation interchanging R1 and R2 to D, then we get the matrix 35, 52, 27, 40. And here we see that these two matrices are not equal. So this is actually consistent with our hypothesis, where we said that if we apply a row transformation to a matrix and the matrix is on the left of the multiplication sign, then equality is maintained if we just apply the same row transformation to the product, the original product of the two matrices. However, if the matrix is on the right of the multiplication sign, equality cannot be maintained by applying the same row transformation to the original product. I have more examples here. This is the second type of row transformation where you multiply a row by a constant. I have chosen R1 becomes half times R1, which gives us the matrix half 1 3 4, and you can see that when we apply the same row transformation to C, it is equal to the new product. It is equal to the new product, and when we apply the same row transformation to D, it is not equal to the new product, BA. Same is the case for the third type of row transformation. Here I have chosen R2 becomes R2 plus 3R1, which changes the matrix A to 1 2 6 10, and these two matrices come out to be equal while these two are not. Moving on to matrix B, if we apply the same row transformation, R1 and R2 are interchanged to B, we get 8 9 6 7, and that changes our product AB to 1 2 3 4 times 8 9 6 7 instead of 6 7 8 9, and that comes out to be 20 23 48 55. If we apply the same row transformation to C, and we've done this already, so you'll remember it turned out to be 50 57 22 25, and these two matrices are obviously not equal. Let me change back to green here and do the same test for the new product BA, which has changed to 8 9 6 7 times 1 2 3 4 instead of 6 7 8 9 times 1 2 3 4. This turns out to be 35 52 27 40, and when we apply the same row transformation to D, interchanging R1 and R2, we get 35 52 27 40. Once again, it's clearly visible that when we apply a row transformation to a matrix, the equality is maintained if we apply the same row transformation to the product, only if the matrix is on the left of the multiplication sign. However, if the matrix is on the right of the multiplication sign, equality cannot be maintained by applying the same row transformation to the product. And the other two types of row transformations are shown here, and I'll give you a moment to look over the results, but it's consistent with our hypothesis, it's consistent with our earlier findings. If the matrix is to the left of the multiplication sign, then a row transformation can be applied on the original product to maintain equality. If it's on the right, it cannot be the equality cannot be maintained if we apply a row transformation on the original product. Coming to column transformations, let's apply a column transformation on A. Let's interchange column 1 and column 2. That gives us the matrix 2 1 4 3, and that changes our product AB from 1 2 3 4 times 6 7 8 9 to 2 1 4 3 multiplied by 6, 7, 8, 9, which comes out to be 20, 23, 48, 55. If we apply the same column transformation to C, then we get the matrix 25, 22, 57, 50. And these two matrices are also obviously not equal. Now let's change back to green and see what happens to the product A, which has changed from 6, 7, 8, 9 times 1, 2, 3, 4 to 6, 7, 8, 9 multiplied by 2, 1, 4, 3. And this comes out to be, this comes out to be 40, 27, 52, 35. And when we apply the same column transformation to D, C1 is interchanged with C2. Then also we get the matrix 40, 27, 52, and 35. So here we see that if we apply a column transformation to a matrix, then the equality can be maintained by applying the same column transformation to the product if the matrix is to the right of the multiplication sign. However, if it is to the left of the multiplication sign, equality cannot be maintained by applying the same column transformation to the product. There are two other types of column transformations, and I've tested them out here. The results are consistent. Once again, when A is on the right of the multiplication sign, then equality is maintained. However, when it's on the left, then equality is not maintained. Same case for the third transformation. Let's apply column transformations to matrix B now. We'll be applying column 1 interchanged with column 2, which changes B to 7, 6, 9, 8. And it changes the product AB to, it changes the product AB to 1, 2, 3, 4 times 7, 6, 9, 8, which is 25, 22, 57, 50. And when we apply the same column transformation to C, then we get 25, 22, 57, 50. And we can see where this is going if we check what happened to our product BA from 1, 2, 3, 6, 7, 8, 9 times 7, 6, 9, 8 into 1, 2, 3, 4. And this evaluates to 25, 38, 33, 50. Whereas if we apply the same column transformation to D, interchanging column 1 and column 2, we get 40, 27, 52, 35. And this holds true for the other two types of column transformations too. When B is on the right of the multiplication sign and a column transformation is made on it, then equality is maintained. However, when it's on the left of the multiplication sign, equality is not maintained. the same thing happens for the third case. Now what I find this is part of the beauty of maths, I think, but I find this absolutely hilarious. The thing is that when we try to find the inverse of a matrix, the inverse of a matrix is defined as if B is the inverse of A, then AB and BA will both be equal, and they'll be equal. Both of these products will be equal to a unit matrix. And what I love about this is that it doesn't really matter if you're applying a column transformation to, this should be A. It doesn't really matter if you write down this A or not. It's just there on the page. You're not using it for any calculations. And so if you were doing some rough work, if you were calculating this and you didn't have to show the steps to anybody, you could just omit this A and do many column transformations on this to get I, and in the end you'd end up with the inverse of A over here. And the funny thing about this is it doesn't matter if you place A over here or A over here to the left or the right, because you're doing the same transformations on this side and on this side, and whether you do column transformations or row transformations, you're going to get the inverse of A in the end. And that means that if you messed up this equation at the start, you're going to get the correct answer even if you were wrong every step of the way. And that is something that you have to watch out for.